What are the two types of charge? What are the two types of charge? Kevin, what's one? Positive and negative, right? Positive and negative. Where do we get positive charge from? Right? It comes from protons, yes, but not just protons. Anybody be a little bit more specific there, Donovan? Good. You have more protons than electrons. What about negative charge? Where does that come from? Cal? More electrons than protons. Good. Finally, what's that one that's in the middle that we never wrote down yesterday or today, but we talked about? Not neutrons. No. Close. Neutral. Right? Neutral comes from having not just neutrons. Neutral comes from having same number of protons as neutrons. Protons as electrons. Good. Same number of protons as electrons. Good. What about the structure of the atom? Where do those protons and those neutrons and those electrons come from? You got something orbiting around this thing in the middle. What is that thing that's orbiting around, Cal? Good. It's electrons. And the electrons are negatively charged. They have very, very small mass compared to the mass of the protons and the mass of the neutrons. In the middle of this thing, in the nucleus, we've got the protons that are positively charged, and we've got the neutrons that are neutral. Both of those are pretty heavy, about 1,000 times heavier than the mass of the electron. If something's going to move, we're talking about electricity here, right? If something's going to move and transfer from one thing to the other, and something's got to, right? Otherwise, we wouldn't have any kind of phenomenon going on here, no kind of electrical phenomenon. If something's going to move, what is it that's going to move? Is it the protons? Is it the neutrons? Is it the electrons? Yep. It's going to be the electrons that move. Can anybody explain to me why it's going to be the electrons that move as opposed to those protons or those neutrons that move? Jesse? Yeah, the electrons aren't as tightly bound to the nucleus as the protons and neutrons are. There's an electric force that pulls them into the nucleus and tries to keep them a part of the atom. But it's not nearly as strong of a force as that nuclear force that acts within the nucleus, keeps protons together, keeps neutrons together, and keeps protons tied to neutrons. It's a much, much weaker force, and therefore it's a lot easier to overcome. That's why if something's going to move, it's going to be the electrons that move. All right. Does anybody remember the charge of an electron? I hope you don't remember the charge of an electron. I want you to look in your data sheets. Everybody, right now, look in your data sheet and find, please, the charge of the electron on your data sheet. Who's got it from their data sheet? On your data sheet, it actually says the charge of one electron is negative 1e. Well, what does that mean? Negative 1e means, Kevin? No, not an electron volt, no. Shelby? Yeah, it's negative 1 times the elementary charge. If you look on the left-hand side of your data sheet, it says the elementary charge is 1.6 times 10 to the minus 19. So that means the charge of an electron, we'll call it QE. Q is a symbol for charge, by the way. QE, the charge of an electron, is negative 1 times 1.6 times 10 to the minus 19 coulombs, which is negative 1.6 times 10 to the minus 19 coulombs. That's a pretty small number, right? 10 to the minus 19 coulombs. That tells us that a coulomb is a really big unit. What do we say? It takes about 10 to the 19 electrons to make up 1 coulomb of charge. Because of that, we often see charge written not as coulombs, but as microcoulombs or as nanocoulombs. You guys remember what that prefix is, a micro? 10 to the minus 6. If you forget that, that's printed on your data sheet as well. What about this one, a nanocoulomb? Yep. Good. 10 to the minus 9 coulombs. And again, if you forget that, that's okay as well. It's on your data sheet. Just look for it on your data sheet. It's the charge of a proton, by the way. Good. Positive 1 elementary charge, or positive 1.6 times 10 to the minus 19 coulombs. Finally, what's the charge of a neutron? 0, right? It's a neutron. It's neutral. Yeah, that's why it's called a neutron. All right. Anybody tell me the difference between a conductor and an insulator? Yep. Okay, it allows the electrons to travel between atoms. Why is that? You're right. Okay, so far so good. But why is that? Why does it allow electrons to move around? Yep, cool. Yeah, the outer electrons are held onto more loosely than they are in other things like insulators. So you've got this conductor. By the way, what's a good example of a conductor? Silver. So you've got this silver. The electrons on the silver aren't that tightly bound to the atom itself. They're attracted to the nucleus. They're there, but they're not as tightly bound as they are in some other materials. So it's a little bit easier for those electrons to move freely around, to conduct, to move, to conduct electricity. Versus insulators, which those electrons can still leave the outer levels sometimes. They can still move around, but it's a lot less likely to move around in an insulator than a conductor. Okay, hence, the conductivity of an insulator is not zero, but it's much, much lower than the conductivity of a conductor. Good. We had 3 laws of charge next. There was a 4th one, but it didn't really fit with the 3rd one, so we kind of made it separate here. I don't care what order you give me these 3 in. If you give me one of them, raise your hand now. What's one of the 3 laws of electric charge? Jesse? Opposite charges attract. So that means that positive charge attracts negative charge, and negative charge attracts positive charge. Now, we don't have to have charged objects. Okay, you can have a single proton and a single electron, and they will attract each other electrically. Cassidy, what's another one? Good. Like charges repel. Doesn't have to be objects. It can simply be a proton and a proton repelling each other, or an electron and an electron. Having said that, if you have a positively charged balloon with a positively charged piece of plastic, then they'll still repel each other as well. Positive charges, positive objects, they all repel each other. What's the 3rd one? What's the 3rd one, Cole? Yes, but what's the 3rd one? Good. Charged objects attract neutral objects. And it's important to mention that word objects in there. You're going to learn later today why protons don't attract neutrons and why electrons don't attract neutrons, why you need a charged object and a neutral object to be attracted to each other. All right? What was that final law, the one that didn't really fit with the 3 that we just mentioned there? Yeah. No, not conservation of energy, conservation of, close, conservation of, good. The law of conservation of charge, which says, well, same as the law of conservation of anything else, just about, Cole? Good. Charge can't be created and it can't be destroyed. You can move it around, you can transfer it, you can swap it, but you can't create it, you can't destroy it. Cole, the example of that, I think that we gave yesterday, was you're walking across the carpet in your sock feet, you go and touch somebody, you shock somebody. Clearly you transferred charge to that person. They become more negative than they were before. You become less negative than you were before, or more positive. So your charge has changed. Their charge has changed, but the total amount of charge remains the same. It's kind of like impulse and conservation of momentum. The amount of charge of individuals can change, but the total amount of charge in the system has to stay the same, just like the total amount of momentum in the system has to stay the same. Right? Now, there's a lot of implications of that. One of them is when we touch objects together, they want to balance out. So one thing has a charge of, let's say, -5 coulombs. We touch it with another thing that has a charge of +5 coulombs. They want to balance out. Tell me what they're going to balance out to be. Tell me what they're going to balance out to be. Neutral, right? 0 and 0. If we add these up, the total charge becomes 0. If we divide the total charge of 0 by 2, then the charge of each individual one is going to be 0 as well. What if we have -5 and +7? What are they going to balance out to be when they touch each other? Shelby? +1 and +1. We add these up, we get a total charge of +2. That doesn't mean now that each individual charge is +2. The total has got to be +2. Well, how do we distribute 2 amongst 2 different objects? Divide it by 2, and we get +1 and +1. What if we did this? What if we took minus 5, plus 7, and plus 12? We touched 1 and 2 together, then we touched 2 and 3 together. What's the final charge on all 3 of them become? Assuming that the size and shape of these objects is such that they will balance out equally when we touch them together. What's the final charge become? Well, let's first of all figure out what the total charge is so that we can figure out each step along the way if we've got the same total charge. Minus 5 and plus 7 and plus 12 gives me a total charge, I believe, of plus 14. Is that right? Plus 14. If I touch 1 and 2 together, minus 5 and plus 7, what's the total charge among only those 2 charges? Minus 5 plus 7 is plus 2. We divide that by 2, we get plus 1 and plus 1. So when we touch 1 and 2 together, they become plus 1, and then the third one hasn't changed yet, right? It's still plus 12. Let's add these up, and let's make sure that even at the second step here, that we're still at plus 14 for a total charge. 1, 1, 12 gives me plus 14. So far, so good. Now we're going to touch 2 and 3 together. Plus 1 and plus 12 gives me a total charge of plus 13. Divide that by 2, we get 6.5 and 6.5. Can we do that? 6.5 coulombs? Can we have a fraction like that? Yeah. Guys, a coulomb is a huge unit of charge. It's gigantic, right? We can easily have a half a coulomb. We can have a millionth of a coulomb. We can have 100 millionth of a coulomb. Okay, a coulomb is so big that it's easy to get the tiniest fraction of a coulomb. So there's no issue with that at all. Let's add these up just to make sure we're still on the right track here. 1, 6.5. 6.5 gives me 14. So 5 and 7 and 12 become 1 and 6.5 and 6.5. Is that clear? Make sense? All right. That's about where we left off yesterday. Today, we're going to go one step further and talk not only about charges of objects and the characteristics of those charges, but rather today we're going to talk about how objects get charges, how objects become negatively charged or positively charged. There are 2 ways that we can charge objects. One is called induction, one is called conduction. Now, these 2 ways are both very distinct ways of charging objects, very different ways of charging objects. Conduction, charging by conduction, always involves, every single time, always involves a charge transfer. Q means charge, remember, right? Always involves a charge transfer. No exceptions to that. Induction never involves a charge transfer. So if charges, and when we talk about charges, we're talking about protons or electrons. If something's going to transfer, what's it going to be, protons or electrons? Electrons. So if we have electrons transferring from one object to the other, one becomes negative, one becomes positive, it's got to be conduction. Because induction never involves a charge transfer. Now, conduction also usually involves, although not every time, usually involves touching. 2 objects touch each other and charges transfer by conduction because they're touching each other. Now again, it's not always, it's usually involving touching, not always. I'll describe a situation in just a moment where 2 objects don't have to touch in order to transfer charge. Induction never involves touching. So if you have a problem in which charge is transferred, you know right away it's conduction. If you have a problem involving in which charge is not transferred, you know right away it's induction. If you have a problem in which the 2 objects touch each other, it's got to be conduction. If you have a problem in which the 2 objects don't touch each other, It could be conduction or it could be induction. The overriding factor that we look at is whether charge is transferred. Now let me give you an example of conduction taking place when objects don't actually touch each other. Let's go back to that walking across the carpet thing in sock feet again. You walk across the carpet in sock feet, you reach out, you build up a potential difference, by the way, between you and the ground of somewhere in the range of 15,000 volts when you do that. It sounds like a lot, but in order to feel a shock, it's got to be somewhere in that range of 15 to 20,000 volts. It is a lot. Okay? You reach over, you touch somebody, you get a shock. They get a shock, you get a shock. Charge has been transferred, you've touched them, it's clearly charging by conduction. The next time you go to do it, you walk across the carpet, you shuffle your feet, you go to touch somebody, and just before you make contact, what happens? The charge arcs, the electrons arc. They jump from your finger to their ear or finger or whatever it is that you're touching. That's still conduction because charge has still been transferred. But notice it didn't involve touching them. Sometimes with conduction, two objects get close enough that it's as if they're touching and the electrons just jump across the gap. They arc from one to the other. That's still conduction because it still involves a transfer of charge. Now, let's differentiate between the two subcategories of conduction. The first one we call charging by friction. The second one we call charging by contact. Charging by contact, by the way, is often just called conduction. We often don't give it another name. We just often call it conduction. But technically, we should call it contact, even though it doesn't always actually involve touching. Okay, we still call it charging by contact. Friction, okay, I think this is pretty logical. Take two objects, rub them together. What happens? Rub your hands together right now. What do you feel when you rub your hands together right now? You feel a little bit of heat, right? There's energy liberated. You've got kinetic energy as you move your hands, and some of that energy is liberated. If you rub two objects together and one of them has loosely tied electrons, then what's going to happen? The kinetic energy is going to be given to those electrons, which is going to cause those electrons to be liberated and go to the other object. So if they were both neutral objects, you rub them together, the kinetic energy causes the electrons to go from one to the other, making one of them negative and making the one that lost the electrons positive. Friction is as simple as that. You rub two objects together. And electrons move from one to the other. The one that gains the electrons will become negative. The one that loses the electrons will become positive. The law of conservation of charge comes into play here as well, right? If you have two objects that are neutral, you rub them together, one becomes +4. What does the other one become? You guys know this. The law of conservation of charge says charge can't be created or destroyed. Neutral and neutral. Rub them together, +4 and -4, because they've got to add up to give me nothing, right? Add up to give me 0. Charging by contact, which we sometimes just call charging by conduction. Here we've got two objects that we're bringing either close enough to actually touch or just close enough for electrons to arc or jump from one to the other. I'll put in quotation marks, touch two objects. Quotation marks because, remember, it doesn't always technically involve touching. Touch two objects together, electrons move from one to the other. Now there is a condition on this one. They can't be the same charge to start off. Let's think about that. If we have two objects, both that are -5. Okay? Here's -5, here's -5. Bring them together, touch each other, what do they become? -5 and -5. They don't change, right? So we haven't done any charging there because they stay where they were. But if I had -5 and -7, touch them together, what do they become? -6 and -6. So they've got to be different charges to start off in order to charge by contact. If you don't have a difference, you're not going to get charging by contact. We get charging by conduction when lightning strikes. Even though the cloud isn't actually touching the ground, that's still charging by conduction. But lightning doesn't happen if the charge of the cloud and the charge of the ground is exactly the same. Lightning only happens when there's a big difference between the charge of the cloud and the charge of the neutral ground. Right? No, that's a bit of a myth, actually. Yeah, yeah. I mean, the laws of probability would dictate that lightning probably won't strike the same place twice. But the laws of probability would also dictate if I take a dart and I throw it 1,000 times against that wall in the back wall, right, that I won't hit the exact same spot twice, right? Because there's so much area for that dart to hit, I'm probably not going to hit the exact same spot twice. Lightning's probably not going to hit the exact same spot on the Earth twice either, although there's no real reason why it couldn't. Just, yeah, I think it's a bit of a misconception that people think that lightning can't strike the same place twice, only because we haven't seen it hit the same place twice. Because statistics would say that probably never will. But there's no reason why it physically can't, right? Just like, statistically, I'm never going to win the lottery. But it's possible that I actually would win the lottery, right? Most people would say, yeah, you're never going to win the lottery just because I've never won it yet. Okay? And statistically, the odds are against me, right? But it could happen, just like lightning could strike the same place twice. Yep. Yeah, actually, yeah, that's a good point, actually. The Statue of Liberty is struck often, that's not the only place, but that's an obvious one that gets struck often. High buildings all have lightning rods attached to them to attract lightning. Lightning strikes lightning rods on buildings all the time. Okay? Why does it strike the lightning rods? Why does it strike the Statue of Liberty? Well, electrons always take the easiest path to the ground. Well, the easiest path is the highest thing. Right? That's why in a lightning storm, you don't want to be out on a golf course holding a metal golf club up in the air, because lightning is going to take the easiest path, which is through that golf club, through you, down into the ground. As odd as it might sound, if you're out in the middle of a lightning storm, get rid of your golf clubs and huddle up in a ball on the ground, on the flat ground. You're safer doing that, as scary as that might be, than you are running away with golf clubs in your hand. Yeah. Would it be okay if, the question, if you didn't hear that, would it be okay if you were wearing a rubber suit playing golf? No. Don't do that. That's a good point, actually. I'll come back to that in a second here, and we'll come back to it even more detail later on in the unit. But would a rubber suit work if you were playing golf and there was a lightning storm? No. Rubber is a very good insulator. Air is a pretty good insulator, too. Lightning just came from the cloud through a few kilometers of air to the ground. If it was able to go through a few kilometers of air, it's going to easily go through 2 centimeters of rubber, easily. Right? Now, Cole mentioned something. If you wear a metal suit, you should be fine. Well, that is incredibly counterintuitive, but ironically, it's correct. If you're wearing a metal suit in a lightning storm and it's completely surrounding you, you are 100% safe in a lightning storm. You can be struck by lightning and not feel one thing. And we'll explain why that is a little bit later in this unit when we talk about charge. Yeah. When we talk about charge distribution on conductors, you'll see exactly why it's safe to be in that suit of armor. Same reason it's safe to be in a car in a lightning storm, because you're surrounded by metal. As odd as that seems, you think it would be the least safe place to be, but it's actually the most safe place to be. Question? No. Rubber is an insulator. Rubber is an insulator. So if you're wearing rubber shoes, you think maybe you're safe in a lightning storm, right? You get struck, but it's not going to go through your feet, so it's not going to discharge to the ground, so you should be fine. No, it'll leave you. No, it'll leave you. My shoes have, depending on the spot, anywhere from 1 centimeter to about 2.5 centimeters of rubber on the bottom of it. Okay, rubber's a good insulator. Okay, that means that I'm probably, if you walk up to me and you got a bit of charge built up on you, you're probably not going to shock me. Okay? I'm probably not going to discharge into the ground because, you know, I've got a little bit of rubber on my shoes, which is a good insulator. But if I have 6-7 million volts of electricity going through me, the electrons have that much energy, they're going to easily go through the rubber in my shoes, easily. As much as rubber is a good insulator, it isn't that good of an insulator that it's going to keep the electrons from going through. Everyone has this misconception about a car. Everyone's heard the car is a safe place to be in a lightning storm, right? Oh, because it has rubber tires, right? Because it's an insulator. Has nothing to do with that. Has nothing to do with that. Rubber, the electrons went from the cloud all the way down to the car, yet they can't make it through 1.5 centimeters of rubber. Of course they can. Easily, easily. Car is a safe place to be because it's metal. You're surrounded by metal. And again, we'll talk about why that makes it safe later on this unit. Okay, let's get back to the topic here. Talk about induction. Induction occurs, charging by induction occurs when we don't have a transfer of charge and when we're not touching an object. I'm going to flip the page here, draw a picture of this. Let's say we have a neutral object here. I'm drawing it as 4 positives and 4 negatives, but could easily be 4 billion positives and 4 billion negatives. It just means same number of protons as electrons. I'm going to bring a negatively charged object nearby. What's going to happen to the protons in this neutral object when I bring this negatively charged object nearby? As people are raising their hand, I'm going to tell you right now, just so I'm not setting you up for failure here. There is a trick to this question. What's going to happen to the protons as I bring this negatively charged object nearby? Right? They will stay where they are. Why? Something's going to move. It's going to be electrons, not protons. The protons are going to stay where they are. All right. So what's going to happen to the electrons there now? These electrons will move, right? Where are they going to move to? Kieran? They're going to move as far away from this guy as they can. Now, it doesn't mean that all of them will. I've drawn it so that all of them get pushed to the left-hand side. They're not necessarily all going to get pushed to the left-hand side, but enough of them are to create what we call a separation of charge. This side is negative now. This side is positive. The overall charge is still neutral, but we have 2 separate sides, one side positive, one side negative. What's going to happen if we have that neutral object? And we bring a positively charged object nearby. What's going to happen to the protons? Nothing. What's going to happen to the electrons? They're going to go the other way. They're going to be pulled towards this positively charged object. So now we have a bunch of negatives over here with a separation of charge. Negative on the left side, positive on the right side. Why do we call this temporary? We said it's a separation of charge, but why is it a temporary separation of charge as opposed to permanent, Jesse? Good. You take this thing away, you take this thing away, there's no reason for the electrons to stay where they were. They're going to go back to where they were originally, right? Roughly evenly distributed, making it neutral, still neutral, I guess, but with no separation of charge there, right? So it's a temporary separation of charge. One more thing that I want you to look at here. The side of this neutral object that's closest to the charging object is opposite to the charging object in both cases, see? Positive and negative. This one should be the other way around, right? This side is negative and this is positive. The effect of that is that this charged object right here will attract this neutral object right here, because the side that's closest to it is opposite. This charged object will attract this neutral object right here, because the side that's closest to it is opposite. In order to get a charged object attracting a neutral object, we need a charge separation. That's why a proton doesn't attract a neutron, because in a neutron, you can't get a charge separation. A neutron is a neutron. You can't get things separating and making half the neutron positive and half the neutron negative. Okay, neutrons are not attracted to either protons or electrons because you can't get a charge separation. Does that make sense? Yep. Well, be careful with that. Be careful with that. A lot of people, most people associate poles with magnetism, right? And electricity and magnetism aren't the same thing. So we're not talking about a north pole and a south pole. It does develop a polarity. Sometimes we can say it's polarized, okay? But I wouldn't want to say poles, because that kind of infers magnetism, right? Definite positive side, definite negative side, but nothing to do with north pole and south pole. Okay? All right, so we said this is a temporary separation of charge. The other thing that we said can happen here is a permanent charge. How do we take this diagram, diagram number 1, and make it permanent? We're going to attach what we call a ground wire. Now, a ground wire can be literally a wire that goes from this object into the ground. Or it could be something like me touching the object, the other end of me connected to the ground, me providing the conductive path from the object to the ground. Or it could be any conductor that provides a path from the object to the ground, or something that's really big and can act as the Earth. The Earth effectively is what we call an infinite source and sink, Michael, of electrons. That means that we can take as many electrons as we need to from the ground. We can add as many electrons as we need to the ground without really affecting the ground. So let's attach a ground wire here and see what happens. That's the symbol, by the way, for the wire or whatever conducting path going right into the ground. What's going to happen here? Bring this negatively charged object nearby. It pushes the electrons to the far left side. But if there's a ground wire there, they don't stop on the far left side. They keep going right into the ground. What does that do to that thing that was neutral? The thing that was neutral is now positive, right? It's now positively charged. But it's still temporary, because if I take this away, what happens? The electrons are going to come back where they came from, and it's going to be neutral again. So what do I have to do to make it permanent? Before I take this away, I've got to disconnect the ground wire. Cut the wire. The wire is cut. The electrons want to come back up and balance it out, but they can't. There's no path for them to come back up now. So now I've got an object that is permanently positively charged. Kevin? That's a good question. Kevin just said, could the rod arc electrons over here? Yes, it could. But if it does, that's not induction anymore. If the rod arcs, if the rod comes close enough to arc electrons over to the neutral object, it's not induction. That's conduction now, right? So we have a completely different process going on if that happens. Okay? It could happen, but we're going to say within this process it's not happening, because if it did, we'd have to go back to what we were doing before, which was conduction. What happens here? Touch this ground wire. It's not going to push electrons down into the ground, is it? Because it's sucking electrons over as close to this object as we can. So what happens? Yeah. Electrons are going to go up from the ground Get a bunch of extra electrons in here. Now what happens to this? It's now negatively charged. If I cut that ground wire, now it's permanently negative. Because although the electrons want to go back down into the ground, they can't. They have no way down. Does that make sense? When I went to university in 1990, I lived for my first 2 years on campus, which, by the way, I would highly suggest to everybody, living in dorm for a couple of years just to get the experience of residence life. But then you get a little tired of that after a while. Moved off campus after 2 years with 4 of my friends, 5 of us, in a 5-bedroom house. This 5-bedroom house was a dump. I guarantee you, you have never lived in a house like this. You have never probably been in a house like this. You have probably never seen a house like this. Certainly not on the inside. The floors were crooked. The center of the house was the high point because there was an old fireplace there with concrete. So it was kind of like a bit of a foundation there. But the rest of the house was just sitting on the dirt. So it was sinking into the ground. If you put a ball where the fireplace was, it would roll to one corner of the house, like quickly, because it was quite a difference in the height. The stairs in this house were about this wide, which meant that every time you'd go to run up the stairs because you were late for class and you forgot something in your bedroom, you'd slip and fall down the stairs. The railing at the top of the stairs was about this high. It was like the stairs and the railing was like it was built for, it was like miniature land. Like it was. The wallpaper in the kitchen, this was great actually. The wallpaper in the kitchen was a pattern from I don't know when, like 1950 something or 60 something. It was some old flower pattern, which was great because when you had spaghetti fights, it just kind of blended in. You never really noticed like that there was spaghetti on the walls. It just kind of blended in with the pattern that was there. The living room, this was great too. Guys will appreciate this. You go to watch a football game or a baseball game, the living room wasn't carpet. The living room was AstroTurf. So it was great because it kind of a little bit felt like you were there when you were watching a football game. And you could spill things and it kind of just went away. I don't know where it went, but it never really made a mess. So we didn't have to clean very often or ever. There was some positive things about the house, definitely, even though it was a dump. I'm sure our parents were terrified every time they left the house, and I'm sure they're like, oh, I can't believe my son is living in this place. They're going to die before I see them next. I'm surprised we didn't, actually. I'm really surprised we didn't die before we saw them next, because one of the things that was quite serious, actually, although we didn't appreciate this at the time, was the wiring in the house. The house wasn't grounded. I mean, that's electrical code, and it's been electrical code for years and years and years and years and years, that houses have to be grounded. You have to have a third prong, right? 3-prong plugs. If there's any kind of arcing, that drains excess electrons to the ground, like literally into the ground, and prevents a fire from taking place in your house. Well, we only had 2 prongs in all of our plugs. Whenever we wanted to plug something like a computer in that had 3 prongs, we just went and bought a cheap extension cord, ripped the 3rd prong off the extension cord, plugged it in, and then plugged the computer into that, which wasn't good for the computers either, because it's not safe for fire, but it's also not good for your computer to not have it grounded. Anyways, I remember one night very clearly. It was, I believe, my 2nd year in this house, and there was 4 of us sitting around the kitchen table, and then one of us, the 5th guy, over here by the stove, cooking his own supper. We always used to cook our own supper because otherwise, whose ever turn it would have been just cooking KD we would have KD every night probably if we took turns. the stove is right there. We're eating. 4 of us are eating. One guy is over here cooking supper at the stove. Here's the refrigerator over here. And the house is shaped like this, so that the entry to the house is kind of over here. You'd walk between the fridge and the stove. This wasn't very wide, but it was wide enough to walk between the fridge and the stove to get to the entry of the house and then walk into or out of the house. Anyways, the one guy, his name was Mo. We called him Mo. I'm not sure why, because his real name was Nick. But for whatever reason, we called him Mo. Anyways, Mo was flipping stuff on the stove and cooking whatever he cooked, was cooking whatever, and he got a shock. And I mean, most times people get a shock. It's, you don't really pay too much attention to it because a shock is, people get shocks, right? People get shocks all the time. So it wasn't really a big deal. He announced it. I just got a shock. But nobody really paid too much attention because people get shocks. So then he gets another one a few minutes later, and then he gets another one, and then he gets another one. And now he's trying to figure out what's causing these shocks. And for the life of him, he couldn't figure it out. He's touching everything, right? Everything on the stove, everything on the fridge, and he can't figure out what's giving him the shock. And then by accident, he discovers that as he's flipping the frying pan over here, touching the stove, flipping the frying pan, and he goes to open the fridge door at the same time, when he touches the fridge and the stove at the same time, that's when he gets the shock. And it gets better, because he discovered the shock lasts as long as you touch the fridge and the stove. So it's not just an instant thing like, you get a shock like you get when you walk across the room and touch the light switch. The shock will last indefinitely, as long as you touch the fridge and the stove at the same time. So now, there's 4 guys sitting around a table that were rather disinterested in this whole shock thing, but now all of a sudden are paying attention. Now, you know what girls would do at this point? Call an electrician. You know what boys would do at this point? Get their stopwatches out and see who can hold on the longest. At first, it was literally half a second. Over several weeks, we were able to build up to, I think we got as high as about 2 minutes, I think. We were able to hold on to about 2 minutes. It's quite, it was a nasty shock too. It was a bad shock, but you built up a tolerance to it after a while. It's kind of like, you get headaches all the time, you take Tylenol, you need to keep taking more and more Tylenol to have the same effect. It's kind of the same thing. You build up a tolerance to electrocution. So this is what would happen actually is, we all had classes at different times of the day. You'd get up in the morning and sometimes there'd be this piece of paper on the fridge with the guy's name. It would say, Mo, 37 seconds. So then it's like, well, oh geez, Mo must have hit 37 seconds this morning. So then it's my turn to try to get 38 or longer. So it was odd because sometimes you'd be there all by yourself in the kitchen just holding onto the fridge of the stove, timing yourself, trying to beat the record. After a while, we got kind of a little bored of it, but it lasted for a few weeks before we got bored of it. Anyways, I was the physics student, so of course, the question always came to me when stuff like this happened, like, well, why is this happening? What's the cause of this? And at first, honestly, I had no idea. At first. I was just enjoying the moment, at first. But then it came to me that the house isn't grounded. So what happens when the refrigerator is running and there's moving parts within the refrigerator and these moving parts rub against each other, they rub against the air, what happens? You get charge transfer, right? Charging by friction. You get a buildup of charge. But if it's not grounded, where does the charge go? Nowhere. So you get this buildup of charge in this refrigerator. Normally when you open the refrigerator, it's not a big deal because you're standing on an insulated wooden floor. But when you touch the fridge and the stove that has a gas pipe that goes from the stove, it was a propane stove. Okay, out here we have natural gas, right? Out east it was propane, okay? Propane pipe goes from the stove through the ground to a propane tank, a big propane tank in the backyard. You wouldn't think, but it worked out okay. All of a sudden, when I touch the fridge and the stove at the same time, I'm now providing a grounding path. I'm now providing a path for these extra electrons on this refrigerator to go through me, through the stove, through the gas pipe, into the ground, and then that's where they stay. They never make it to the propane tank, right? Because the gas pipe goes into the ground. So so we're effectively grounding the refrigerator whenever we touch it and touch the stove at the same time. Does that make sense? And you never thought there were practical applications of physics, eh? I went back to that house. It doesn't exist now. They literally tore it down last year, just literally last year. It should have been torn down before we were there 20 years ago. 22 years ago. But they tore it down last year, literally. It was 2 or 3 years ago. I think it was 2 years ago. I was there. I was in Antigonish, which is where I went to University of Antigonish, Nova Scotia. And I drove by, and it's still there. It still needed a paint job just the same as it did 20 years before that. I thought, you know what? I'm going to knock on the door. I'm going to see who's living there, and I'm going to ask them, can I touch your fridge and stove at the same time? I knocked on the door. Nobody answered. I had my son with me at the time. He was 8 at the time, and nobody answered. So I tried the doorknob, and it wasn't locked. So I opened the door and I said, "Hello." I announced that it was there. Is anybody home? And nobody answered. So we went in. It wasn't lived in. It was abandoned. Nobody lived there. The fridge was in the middle of the kitchen floor. The stove was pulled out from the wall, not connected, so there wasn't even any point in trying to touch the fridge and the stove at the same time, which was really disappointing. Really disappointing for me. I was looking forward to, some 20-year-old student opening the door and saying, "Can I touch your fridge and stove?" and maybe split a 6-pack of beer and see how long. I bet I could beat that kid too. Anyways, we got out afterwards. My wife said, "You know what you just did?" I said, "What?" She said, "You just broke into a house with our 8-year-old son." No, I didn't break in. Break and enter is when you break something to enter. I entered, but I didn't break anything. Anyways, there are other, perhaps more common applications of this stuff that we're talking about here as well. This is what we call an electrostatic precipitator. It's an air filter. It filters out dust from the air. So how does it do that? Well, you've got a battery here. A battery down here with a negative side and a positive side. You can see them labeled. That battery causes these blue rods. You can't really see those labeled. I can from where I am, but from where you are, you probably can't see that these blue rods are charged negatively because they're connected to the negative side of the battery. These red plates are charged positive because they're connected to the positive side of the battery. There's a fan over here. This fan blows air, including dust particles, through this electrostatic precipitator. As these dust particles, these green dust particles, maybe they're moldy, I don't know. They're green dust particles. They blow through this negatively charged rods here. What happens to them? What happens to these neutral dust particles as they touch these negative rods? They become negative. So now these dust particles aren't neutral anymore. Now these dust particles are negative. What happens with these negative dust particles that are now blue? They move through these positively charged plates. Opposites attract and they stick to the plates. So now the dust that was in the air over here before the filter gets attracted to these positive plates and it stays there. The air goes out the other side minus the dust particles. See if you've got cleaner air. Now, every once in a while, you still have to clean those plates, right? Because you've got a whole bunch of dust building up on it, a whole bunch of pollutants building up on it. But the air coming out the other side is purified, at least to some degree, is purified. Does that make sense? Here's another one. This is electrostatic painting. Electrostatic painting doesn't mean you're firing electrons or protons or whatever at a fence to paint it. It means that you're firing paint at a fence to paint it. But this paint gun has a little rod inside it that's either positively charged or negatively charged. Doesn't really matter. We'll say it's negatively charged. What happens to this paint as it blows by this negative rod? The paint becomes negative. All right, so now over here we've got this fence that we want to paint that has been grounded, okay? Largely because it's stuck in the ground, although if it's not actually connected to the ground, you would want to ground it. You have this negatively charged paint that's coming out this gun here and coming towards this neutral fence. What happens? It gets attracted to it, right? It's more likely to stick to the fence because the negatively charged paint is attracted towards it. Now the beauty of this method, take a look at this. Here's the paint coming out the nozzle at the end. You can see that obviously the paint that's going right towards, the fence post is regardless of whether it's attracted electrically to it or not, it's going to hit it and it's going to paint the fence, right? But look what happens to this paint that goes up here. It gets attracted to the back side of the fence. So you don't get very much waste at all. You can take a paint sprayer to paint this fence and you don't end up painting the deck beside your pool, or you don't end up getting any paint in the pool because virtually all of the paint is attracted to your fence or to whatever it is that you're painting via electrostatics. Does that make sense? Now the same thing would work if this paint was positively charged, right? It doesn't have to be negative. It just depends upon what the charge of that rod is inside there. Yep. Yep. Make sense? Okay, we got 2 multiple choice questions to work on. I'd like you to do, please, multiple choice number 37 and 38. We still don't have your booklets copied for you, so just take a peek up here. And then send me those answers as multiple choice number 1 and multiple choice number 2, please. One response, okay? One response this time. Submit both of them together. One is multiple choice number 1 and one is multiple choice number 2. All right, guys, let's take a look at these. Number 37 says, the bottom of a thundercloud usually becomes negatively charged. Before lightning strikes, the charge on the ground directly beneath the thundercloud will become what? So here's the bottom of my thundercloud. It's negatively charged. Here's the ground down here. These negative charges within this thundercloud are going to push away negative charges in the ground. Right? The ground is effectively neutral. But these negatives are going to get pushed away so that the negatives are down here somewhere. The ground directly beneath the thundercloud will become positive by, how do you know it's induction? Yes, it is. It's temporary separation of charge. The overriding decision, the overriding thing that makes our decision for us is that no charge is transferred. Okay, we haven't transferred charge from the cloud to the ground. This is before the lightning strikes, right? No charge has moved before the lightning strikes. It's got to be induction, and it's going to be opposite to the thing doing the charging, opposite to the cloud. So it will be negative, it will be positive by induction. The answer will be A, which more than 3/4 of you said, which is good. 38, we didn't do quite as good on this one, quite as well on this one. During the downward lightning strike, what happens during the lightning strike? Well, electrons are going to go down to the ground. It's a negatively charged cloud, at least the bottom of it is. The electrons are going to go down to the ground. That's a transfer of charge. Right away, we know that's what? Induction or conduction? Conduction. So it's going to be either B or D. 45% of you said B, 41% of you said D. So most of you recognized that it is conduction. but it was about 50-50 whether it was negative or neutral. If these negatives come down from the cloud to the ground, what's that going to do to the ground? Or to the tree, for that matter. The ground or the tree. It's going to make it, it's neutral right now. We got a separation of charge, but it's overall neutral. If you add negatives to it, what does it become? Negative. The answer is B. All right? We feel okay about those? All right. That's it for the day, guys.